Hello all. So today we will start binary tree. We'll read about binary tree and a lot of things we'll discuss in this class. So So first of all, what exactly is binary tree? I mean, as you all know, the structure of binary tree is actually kind of like this, right? So it's another data structure, right? It's like another data structure, but it is a non-linear, right? So some key points that basically this involves the formation of data structure in a hierarchical way, right? Hierarchical way we can say, as in that let's say that you can just uh, basically you can just write here. You just quickly write some points for you. It is hierarchical data structure. Fine. Wait. Yeah. Hierarchical data structure. Right. One point. It is non-linear as you can see that. Let's say that in uh, in arrays in arrays usually how was the data structure exactly. It was like it was in a linear form, right? The one thing was pointing like linked list, basically linked list. This is linked list. It was linear way, right? And also in basically in arrays you can see it followed a linear structure, right? Linear structure. There was no different pointers and all, right? Here there is like you can see that there are nodes here, and basically this is what like these things, these are called as nodes. Fine, these are called as nodes. And yeah, so it is non-linear in nature, right? It is hierarchical data structure. And also why it is called binary, by the way. So this like really a simple way. Like binary means that one and zeros, right? So it basically means that binary tree has nodes, right? Like this has nodes, and it is a binary because it can have two things, not more than two. It can connect to two only, two nodes as well, right? So hence, and binary means one and zero, two. So hence this can be 1 0, basically just the way that it is called binary, right? So that's the whole buzz about it, why it's called binary, right? And a real world example can be that you can just basically when we are dealing with the folder structure. Let's say that we have some folder, right? Let's say we are in our C drive, right? We are in C drive, and then you know that you let's say that you are using terminal. You use cd command to just go inside that folder, right? You will find another folder, and then if you basically if you do cd again, right? Maybe you will find two other folders, right? Two other folders. We have folder or maybe one file will be there. So basically this structure is also kind of like a graph, right? So one real world example can be in this way. Fine. And some basic terminologies which you guys should know. Okay, so basic terminologies. Yeah, I yeah, basic terminologies. So let's say that uh, let's draw it a little better this time. Yeah, right. So we have these nodes basically, right? Yeah. uh, Let me quickly make them. Yeah, so it's yeah, so let's say that this is a binary, right? You can see. So when like even in this lecture or in general, you should know that whenever we are seeing the root, so the first this is called as root. Got it? This is called root, right? And these two things, right? These two nodes, which like this is a parent, right? So these two roads are called as children, right? Just like a children and parent relation, right? So this is a children. This node, let's say that this A, B, C, right? So B is a child. B and C are children of A. right? You can see B and C are children of A, and A is the parent. Fine. And you can say that these the nodes which are, you know, at the last, these are called as leaf nodes. Fine, these are called as leaf nodes. And also subtree, let's say that this is a tree, right? But if you see this, let me just, let's say that this part right here, this is called as subtree. Fine, you can say this is a subtree because it's a tree inside a tree, right? Even if you consider a p node, then this will be a subtree, right? So just write subtree. Fine. And what else, ancestors. So basically, let's say that this is D, right? So for D, A is ancestor, A or whatever note like B and C, A, B, C. So for D, like these are the ancestors, right? So the above levels. Fine. Also, these things like this, these are levels. These are called levels, right? I will just also draw that for your convenience. Let's say shift. Yeah. This wait. This is also one level. This is also one level. Right. And this is also one level. You can say that, let me just select them as well, white color and opacity. Yeah. So these are the levels. Fine, these are the levels, you can say these are the levels. Fine. So yeah, so basic terminologies clear, all clear. Fine. So let's move to the types of uh, binary trees, right? Types of binary tree. Fine. uh, yeah. So in general, there are basically a lot of types of binary trees. So first, I will also draw them. Let me just quickly mention all the trees. So overall, there are four types. We will discuss these four types, right? So talking about the full binary tree, right? So full binary tree, let's write here. Full binary tree basically means that, let's say that the there should be, for every node there should be either zero or two children, right? Let's say that we have this binary tree, right? uh, we have this binary tree. So basically this is a full binary tree. For every children, for every node, there are either zero or two trees or two nodes, right? Also, this is also binary tree, right? So every node has either 0, yeah, 0 or 2, 1, 2. So this is a full binary tree. Fine. Complete binary tree means that all levels are completed and except the last level. Or maybe the last level should, like, basically last level has all the nodes on the left position. That is called as complete binary tree. Let's say that this is a complete binary tree, right? It is complete. Also, if there are some nodes are not there on the last leaf nodes, but it should be always be there on the left side, right? So let's say that this is the binary tree. This is not a complete binary tree, right? Because on the left there's nothing, on the right there's one. So this is not complete binary tree. The complete binary tree, a valid complete binary tree, would be something like this. See, this is a complete binary tree. Fine, this is a complete binary tree. This is a, let me also draw similar full, not a full binary tree. Let's say this is not a full binary tree, right? Yeah. Now, coming to perfect binary tree. Perfect binary tree basically means that, basically it's all the nodes are, filled and all, right? You can just, I will just draw, like this simple perfect binary tree. It's a perfect binary tree, right? So this is a perfect binary tree, right? But this is not a perfect binary tree. If I draw something like this is not a perfect binary tree. right? And then there are degenerate trees, right? uh, better that we degenerate trees are basically just this one more category. Let me draw that. Let me also mention that as well, right? I will make this here degenerate trees, okay, here. And here there's also balanced tree, balanced binary tree, balanced bt. Yeah, so balanced b tree. Balanced b tree means that I will just write a few point that the height is max of log n, right? Like if the height of the binary tree, if there's some height, the it should be the maximum of log n. Basically, let's say that we have, I will give you one example. Fine, let's say we have n is equal to 8. Basically there are 8 nodes, right? So log of 2 base n or 8 is what, 3, right? So basically you can make the balanced tree, so the max height, the height should not be more than 3. Basically height, see, if we have 8 nodes, right, you can fill them, right? So this is the 3 height. You can't make this binary tree, you can't make this binary tree like this, in this manner, in this n. It should be on always log of n, right? So this is right, but this is not a balanced binary, right? So this is just a function, just a, you know, formula you which just shows how this works, right? And degenerate trees are basically this only, you know, skewed trees, you can say skewed trees, which basically will go like this, right? So we won't be dealing with skew trees a lot, and it's not also used anywhere majorly. So yeah, these are the major types of binary trees that you will encounter. Fine, let me just make it little bit visible. Yeah, so these are the all the types of binary trees. Now let's jump to the basically the creation or the coding part of how you can uh, code code out the binary tree, right? So let's go here. I hope my voice is fine. Yeah, okay. So creation, right? So I will be doing that in CPP, but you are free to use any other kind of language as well. But it basically the whole purpose lies the same. So let's say that we have one node class, right? If you have seen my linked list thing, right? So please go and watch the linked list so that you can know the structure is really very similar with this. So LL, please watch that before seeing this, right? So class node, let's say that we have one node class, right? And I want to create one public, right, inside it, and I want int data, right? What exactly we want in a binary tree, let's also see that side by side, right? So let's say that this is one, this is called as node, right? This is called as node, and we have two other nodes which are connected. Basically two pointers are there, right? And L and R, left and right nodes, right? So similarly we will code out. So but in data, in data is basically what data the node has. Like we are just writing the properties of the node, right? So wait, yeah, in public, yeah, in data, right? Now we will write node star left node, basically what needs, what we exactly need, right? Left and right nodes, so we'll write them. And then we will also make a constructor, basically, right? It's just a normal constructor, right? If you're familiar with the constructor concept, then it will be good, perfect for you. This data, if you are using, if you are using Java, right? So if you need to basically point out what is this, you don't use this, you can use, I mean, instead of using arrow you use a dot, right? So that's a, like, the small difference basically in CPP, right? So in Java basically you use dot, right? So you can use this dot data, and this dot basically means the arrow. So whenever I'm doing the arrow, it's in the CPP. In Java it is equivalent to the dot, I guess, a really basic thing. So let's get back to the coding part. This dot data, which is equal to D, right? Because that's the data we are defining, and this left, we will now write for the left. So first of all, let's just draw, let's just make it null for now, right? Because it's a generic node, right? What we are doing exactly, see, wait, semicolon, see, we are just defining one exactly node which has both L and R as null, right? It does not have anything, so that's what we are doing right now. Fine. So yeah, uh, this is done. Fine. I will close it. Close. Now writing the node. Right. Now we will just make a build tree. Right. It should have one root, and let's say that this is some function. Right. Uh, as I told you that every binary tree starts with a root. Right. So root should be there. Yeah. So this is, let's say that this is basically what we are making a binary tree which is like this. Wait, let me also draw that. We are making a simple binary tree, right? Like this, and these are, let's say, pointing to null basically, right? Pointing to null. This is a root, right? So now we will write the code for the root. So that's why I'm just passing root, right? It will just initialize the creation of a tree. So in data, right? And I'll be using recursive approach for this, right? If you have seen the recursion video, you know, it's just a function calling inside a function, and yeah, so it will automatically create the for the left and right nodes. So let's say that root is a new node. Basically we're just calling using the constructor, right? New node which will be containing data, and if data is equal to -1, basically just return null, right? Yeah, this will, right? And if root left, now I'll be using recursion for this, right? Like let's say that, okay, let's say what I'm here doing is I have one this, right? I have defined node. I have used some, you know, some code to basically make this node, right? Now if I have L R, right, I can use the same function to make this, so it will basically call it again, make another node, right? And this will just go on and on, right? And if I call the same thing, this will also make the nodes, right? So this is what I will do using recursion only, right? Because the build tree, using the build tree function, right? So root left, what it will do, it will call the build tree function which will have root, what data, which data it should have. I mean, as a root, we are passing the left root, left node, right? So again, right, we will be calling as, and then it's done, right? And just return the node root, or original root basically. So yeah, this is how basic how we make the code, the binary tree, right? So this is what you need to know, creation. um, yeah. So as I told you, we will be basically, now we will see the traversal methods which are used in in this thing, right? Let me just go a little down. Yeah. So yeah, so traversal techniques, we will learn about BFS. So basically there are two ways, BFS and DFS, right? So we'll start from DFS, which has more three ways: in order, pre-order, and post-order, right? So yeah, I think I will use this to explain. place a pointer. BFS, TFS, these three, right? So okay, so basically what in order says, exactly, let's also write it somewhere. Yeah, so in order says that left plus root, or maybe I should write in this way, L plus root, L plus root, yeah, and plus right. How, what does exactly this means? Okay, so let's say that we basically we need to traverse it in this way. So starting from here, so this is a route, right? So we'll go from left, we'll to move to left now, but for this is subtree, right? For so 2 is basically a route for this subtree, so we need to start from L, right? So we will go here, we'll go here, we will see, okay, this ends, right? So this is left, so we will write 4, first 4, right? We'll write 4, then that's done. Now right, then sorry, root, right? So we'll go to 2 basically, right? So hence we will write then what, we'll write 2, 2, right? 2 is done, then right, which is 5, so 5, right? Similarly now we'll go back to 1, so left, so this left subtree part is done, right? So we'll write root, which is 1, right? Now coming to 3, 3 is a root, no, so we go to left, 6, 6, then what, root, which is 3, and then 7. So this is a in order traversal, this will be in order traversal, fine. This will be in order traversal, let me write it a little bit more clearer. This will be in, fine. Now let's write for or maybe I will write it in a better way. Yeah, so here you can just refer what we are doing exactly, right? Now coming to pre-order, what exactly pre means, so you can also just for your reference you can see that if there's in order, so root will come inside it, right? L and R, left right inside it. So pre means that root will come before left, right? So this means root, left, right, right. And similarly post means root will come after L and R, right? So L, R, and then root, right? We'll see for all, right? Now for pre-order, root, left, R, right? Root, left, R. So root, we'll start from root, so 1 is a root, so we'll write 1, fine, we'll write 1 here in the pre, right? Now we'll go to left, which is 2, 2 is also a root basically, right? So we can write 2 here, right? And then coming to 4, 4 is not a root, so it's actually a left, right? So we can write easily 4, and if L is done, then R, right? So 5. So this is done, 5 done. Now root, now coming to root is done. Now 3 is a root, right? So we'll write 3, then again 6, 7, basically same thing. Now for for post order, post means first left and R, so 1 is root, no, 1 is root, right? So we'll go here left, 2 is a root also, right? Yes, then 4, start from 4, you will start from 4, then what, then 5, because left right root, left right root, right? So 4, 5, then again 2 is not a root, is basically not a root for now, right? But left right root, so we'll write 2. So this is done, since the subtree is done. Now we will go to 1, right? So this left is done, but we need to do the right also, right? 1 is root, so but this should be done after its right, because L R root. So we'll go to 3, 3 is also root, so 6, so we'll write 6, then 7, 6, 7, 3, and then 1, because root will come at the last. So yeah, this is how all the traversal techniques for the DFS for now. Now for BFS, it's actually really easy, I don't even need to write it separately. Let me just show you. For BFS basically, right, breadth first search, right, or traversal, breadth first traversal, not exactly search, def first search I have written, it is actually a traversal, but okay. Yeah. So BFS, we will it's actually breadth first search, so it goes from then these, matlab, these levels, and then these levels, so it is easily like 1 2 3 4 5 6 7, so level wise. That's all. That's a simple BFS. So BFS done, DFS done. So this is how the traversal techniques are. Yeah. Now, uh, now we will see the code for every traversal techniques. So I have written three codes for BFS. First one is the pre-order. Second one you can see in order. The third one is the post order. Basically, this will be post order. Let me just correct it. Post order. Post order. Yeah. So yeah, it's done. Post order. Yeah. So you can see that it's just like I'm just using recursion here again, right? See, like if the node is null in all the three cases, just return it, right? And if the, so first you need to print the root itself, right? So we have pre-order, right? So root left r, in this you saw that, right? Left, uh, the pre root comes first, then left and r, right? So we will be printing the root, right? And then we'll basically call this function again, right? Until the node becomes null, it will just call and call, and at the end it will just make this these things, this series, right? So this is how in order will work and post order will work. It's actually really self-explanatory. If you follow this code along with my explanation, you'll get the whole point of this. So just keep a note of it, right? It's a simple way. Now we will see how we can basically do the level order, right? Level order. So let me just quickly write level order traversal. This also important traversal that you should know if you are doing binaries, and it might be useful in your interview rounds as well. Fine. So let me just copy this tree as well, right? Which I have made. uh, yeah, done. This is done. So we have this tree, right? What will be the level or traversal for this? So as I told you before, that levels are basically, this is level 0, this is level 1, this is level 2, right? So level 0, L0, L1 and L2, we call it in this way, level 0. Fine. So if you need to do level traversal, basically you need to return it in this way: 1 2 3 and 4 5 6 7, basically, right? So this is how level order traversal is, basically as much direct. So we will so basically, to code this out, we will be using a data structure q, right? So why q, you will understand that. So let me just, this is the level order traversal. Fine. And I will just erase this, I don't need. Yeah. Now I will be using q for this. How q will work here, let's find out. Let's say that I have q here. Fine, I have one q, right? So first we will start from the root, we will go with the root. As we have some node, we'll put it in 1. Basically we are putting this in one thing, right? And there will be another, basically another vector, or you can say vector, yeah, let's say a vector only, which just stores traversal. Basically what all we are traversing, it is just storing traversal, because we need to end it as we are changing the level. We need to track that, right? So we are just storing the traversal here, right? Vector. So like as I have written 1, right? 1 is done, right? So as I have popped it out, I will pop it out, and if I'm considering 1, I will see if it has left or right. It has left and right, right? It has left and right. So I'll also put it in the this queue, right? But then I will pop 1, and I will just write it in 1 as it is visited, it has been visited. So 1 has been visited, 1 will be one single, it will be stored in this vector, right? So 1, now this is done. Now we are here 2 3, we are here at 2, basically we are considering 2 now. So seeing that 2, we have we will just put this like this, right? uh, we will basically be considering it as a pair because we have, we have uh, we have inserted it in a similar way, right? 2 and 3 have come after 1, so we'll be considering it in this way only, right? So 2 3. Now we'll see for 2, how many are there any left or right nodes? Yes, so we will also put it 4 and 5, right? So 2 and 3, it's done. So here, yeah, for 2 we have done this 4 and 5. Now considering for 3, right? Because we are just 3 3, it will be 6 and 7, right? So we will also push 6 and 7 here. Got it? 6 and 7 will also be pushed here. And basically we will be writing, we will, when this has been popped, we will just basically write it in this way, 2 and 3, right? Now in this queue, let me put, make this little bit lower. Yeah, so now this 4 5 is done, right? Now consider 4, is 4 basically, is 4 there, is, does have a left or right? No. So yeah, just basically, it does not return anything. 5, no, nothing. So yeah, 6 also same, 7. So we'll just return it, return the whole thing together, 4 5 6 7. So now you can see 1 2 3, we just got this what we wanted, 1 2 3 4 5 6 7. So 1 2 3 4 5 6 7, right? This visited array vector, this vector will have our answer basically, right? So now I will just show you the code for this level order traversal once. So this will be a simple Java code for level order traversal basically. Yeah, so what we are doing here is that we're just basically, if the root is null, just return first, and then we are creating a queue as I explained, right? We're creating a queue here. Slow down. Yeah, creating a queue here, and while the queue is not empty, right, this thing will get executed. So we are making one current queue, we are making a tree node called current, and which will be basically a uh, the the pole means that it has been popped out, right? Basically when we inserted 1, right, we started from 1, right, wait, yeah, we started from 1 basically, and then we popped it out, right? So and then we were considering the basically that left, if the current has left or right, right? So we'll pop that out first, right? Write it 1, and then we will check if current dot left is null, then offer, make it left. If current is not equal to null, then just pop the right one basically, and then this just keeps going on and on till the queue gets empty. Like in this case, when the queue was empty, when the whole 4 5 6 7 was in this thing, then just return the basically this vector, right? So you can just write the on your return statements known, and then yeah, you will get the level of traversal here. Got it? You can also basically, this is a void function for now, you can make it a return a vector basically, right? So yeah, this is the whole logic, right? Fine, is it fine? Now we will be basically using, we will be doing the iterative pre-order now. Yeah, just hold, yeah, so iterative pre-order traversal basically. So instead of using the normal recursion, we can also use iterative method, right? And why it's important, just to know what all other methods we can use, right? Let's say that we have one binary tree, right? 1 2 3 uh, 3 here, wait, this is 3, this is 4, right? This is 5, this is 6, and this is 7. Fine. So this is the iterative pre-order. Fine. basically we just need to return how what is pre-order. So it is root left right, right. So this will be 1 2 3, right? And yeah, 4 5 6 7. Basically I have just made it in this way only, just for your understanding. So 1 2 3 4 5 6 7. We will be using stack, right? For iterative approach we will be using stack. How stack? Let's see. Let's say that this is a stack, right? This is a S stack. So the main purpose will be take, just write it, take first, basically the first basically take first right, then take left. So in stack basically when you pop it out, you need to return 1 2 3 4 5 6 7, right? So you need to basically in the stack the topmost element gets popped out, right? So that's why you are using right first. Okay, let's see how. So let's say that we have one stack here, and let me copy it. Yeah, so let's say that we have stack, and yeah, so starting from 1, see 1, and then we will take right first then left. So 1 7 and 2, 1 7 and 2, fine. So as we also need to basically this will be a LIFO, right? This is a LIFO operation for now, right? And we will be popping out as we are writing it. We will be also basically popping out, right? So so yeah, this is the thing. So 1 we have basically considered 1, right? Now checking for 2, we will pop out 2 basically. So 2 we have written. We will check if 2 has something, right? So 2 has nodes. We will write first 4 and 3. We will push 4 and then 3. Now you are seeing the reason why I have written first right and then left, because so that if we are popping out, we need to get 3, right? So 3 will be on top, hence I have written right first then left, right? So 3, then we will be writing it 3, right? So 3 will be here, and 3 does not have anything, right? So we'll just not go with it. We'll write 4 basically here, right? 4, for 4 we have 6 and 5, right? 6 and 5, we are considering 4, right? Now checking for 6, we have some do we have something? I mean first 5, right? So 5, no, nothing. So we will just pop it out, right? 6 has anything? No, pop it out, right? And also just keep writing it here, right? And then left, what is left here? 7. So 7. So this is how we got our this by just a simple LIFO operation. Got it? So I'll be also presenting the code here. So the code would be like in this way basically. Again, simple logic, it's self-explanatory. If the root is null, just return. Now we are using making a stack basically. We are pushing the root first, right? We are pushing the root first, and then while stack is empty, just run this. What we need to run, we need to use the current. Now, as you have seen in the linked list, we were using something called as temp, right? Like let's say that we have some this and this. If we need to do some operations, we had head, right? And if we need to basically use iteration, we had to create some temp, right? We couldn't use head. So similarly here we are using, instead of temp, we are using current here, basically the current pointer which it is pointing to. Alright, so we are using current here, and we are just pushing it like 1. First is current, so we have pushed 1 in the stack, right? And we are just checking, this is just output statement just to print. We are just checking if the current right is not equal to null, then just push the right. If left is not equal to null, push left. This is what we are doing here as well, pushing left and right. And then unless the stack is empty, in this case as well, if the stack is empty, then only print this. Then this just stop, get out of the while loop, and just you can just print this thing, right? Got it? Very easy. Some homework for you all, right? This was iterative for basically this was iterative for your pre-order, right? So you can also similarly, you can just use the same logic to do iterative for post order and in order. Very easy it would be, right, for you. Not much of a work, because the logic kind of remains same. You have to use like stacks. You can use stacks, right? uh, yeah. So yeah, that's how. Now jump going to next question, right? Next question we will jump, uh, which is actually a popular question. It is asked very much, which is depth of pine tree. Yeah, so this is the question. Basically, let me explain you as well, right? So let's say that we have uh, one tree, right? It is in this way. This is one, right? This is two. This is also three, right? And we have four. We have five. Yeah, five here and six here. Let's just, yeah. So this is a bind depth. Now we need to find the depth. What will be the depth of this? This is, I mean, basically we need to just return the levels. How many levels are there in this? Four, right? So we just need to return the max depth basically, which is four, right? What is the depth of the tree? This is what we need to return. So max basically depth. So there are two ways to do this, right? First one is the recursion, and the second one is the level order traversal. You can do simple level order traversal here, just exactly like how we did here. Level order traversal here, we just we can just do the level order traversal and then just return how many times we are iterating. But this will give you time complexity of O of n. Basically I mean, using q you can do this, but it will just give you O of n because we need to go to very uh, we need to basically iterate to all the elements, like all the nodes, so O of n, right? But in recursion basically you can use it will be less time complexity, but it will use auxiliary space, which will be basically O of height, right? If the height is very, I mean, it depends on the height basically. So uh, I mean, you can go, both the methods have its own advantage and disadvantage. This won't take, level order won't take auxiliary space, right? So space time you can compare, but mostly people go with recursion, right? Because we will not be doing we will not be facing this condition. Like, this will get worse if we have this thing, right? If it depends on height, right? So this will be very tedious. But we don't usually deal with skew trees, so we will go with recursion, right? So this is what our thinking approach would be. You can say level order can be counted as the brute force method. Fine. Now also one thought process I would like to share with you all, which will be a very basic pattern for you, right? To basically do any type of mind tree question, right? So yeah. So let's say that we have this tree, right? Uh, yeah. So the logic is, let's say that this current we are at this current thing. This is cur, right? Uh, the we need to find the maximum depth, right? So we can say that this is one level, right? This is one level, this is second level. So let's say that for this thing we have one level plus, right? If we go to left, if this can be anything, right? This part can be anything. Can have some subtrees. If we find some max, basically max depth, okay, let me show you. Let's say that this is some kind of a tree here, right? So this is a one height, right? Also, if you go to this node, this has some height, right? So we need to find the maximum of it, right? So we can say 1 plus maximum of L and R. Let me also write it in this way. This is L, this is R basically. And similarly I can do for r. If I find both the maximum of it, both the heights, and then just put the maximum and then just add for the node, I will get the answer basically, right? This is what I need to find, the maximum depth, right? I will also show you one example. Okay, let's say one example I will give you. Fine, a very easy example. Let's say I have this, let's say that we have this tree, right? And we need to find the depth of this tree using the same logic which we discussed. Fine, okay, let's say that we are here, we are here somewhere, right? We started from 1, right? uh, I'm going, we have 1 plus something. Fine, so basically we have some 1 plus, let's see, we went to this, right? 2, we went to 2, and we saw there's nothing here. 2 does not have any other roads and all, right? So there's only one level, right? So this will return 1, right? This is returning 1 back to it. Now coming to this thing 3, we can see that we have 2 more nodes, so we will go left first, right? 4, right? 4 again has 5 and there's nothing here, so we'll go again down to 5, right? 5 we went here and see that there's nothing here, so we'll return 1. Because 1, why it is 1? Because we are just, this node is also considering a level, right? So we are returning 1 here. Right now 4, you can see here 4, right? 4, what will exactly 4 will have? So 4 has this one and there is nothing in this right node, right? So we can say that 4 basically has this 1 plus maximum of what it has to consider, 1 of maximum of 1 and 0. Left has is giving it 1, right is giving is 0 because there's nothing. So 1 plus max of 0, so this will return basically what? Maximum of 1 is 0 is 1, so 1 1 2, it will return 2, right? In different color it will return 2 here to 3, right? Now see for 3 and for 6 also, if we go, it will just return 1 basically, right? For 3, what will be the case with, if in the left it is coming 2, in the right it is coming only 1, right? So what will be the sum? 1 plus maximum of 2 and 1, 2, 3, 3. So this will turn 3 here, right? Let me write it different color. So this will turn it what? 3. Now finally writing for this 1 plus it is giving 1, right? Which is now maximum of what? 1, which is this blue, right? And then red, which is this 3, which gives me answer what? 1 plus 3, what? 4. Got the answer, main answer 4. Got it? This is the answer. Got it? This is how, this is the same logic which we will be applying here, right? Make sense? Yeah. So I will code this out side by side only, right? So I will write this code, right? So what we are doing here, we are using recursion here, and let's start with find the function max depth, right? Max depth root. Let's say that this just takes some root. Fine, I'm just writing a pseudocode. If root is equal to null, return. Fine. Now int L, basically L, which will be depth. Root, we will be giving it as left basically, right? And int R, we will be giving it, we will just call this, and this will be right. Yeah. And what we are writing this statement, basically this is what we found, right? So we'll be using the same thing here, return 1 plus max of L and R. Done. The question is done. Exactly, this is how, this is the smallest code here, but this had some logic, right? This makes sense, right? So I'll just put it here. Yeah, makes sense. Yeah, cool. Now homework for you guys also, side by side you can just note it down as well, homework, because these questions are really, direct and all. So one is check for balanced tree. You just need to return if the given tree is false or true. Basically, it's a valid tree or not. And one is maximum height and width. This you need to do right now. Like if you are seeing this lecture, just do this compulsory. Then just see the recording ahead. Just we will also now I will just discuss one more question which basically basically derives from this thing. If you have done the height and width to find max and height or width of any question of any tree, then you can do this question, right? So I will just discuss the approach, right? So it's maximum path sum. This is the question basically. uh, Let me make it. Yeah, this is the maximum path sum basically. So here, yeah, so maximum path sum basically, what exactly this question wants us to do. Let's see. Let's say that we have this tree which has some value, right? Let me draw them. uh, this is also some tree, right? Let's say that this is -10, this is 20, this is 15, this is 7. Fine. So basically, there are many paths you can. What exactly is a path? You can go like this. You can go like this, right? You can go like this. So there are many paths. Let's see that one path can be 15, 20, right, and then 7, right? And one other path can be 15, 20, -10, and 9, right? So basically we need to find multiple paths sum. So this sum will be 42, this sum will be something else, but the basically we can find all the paths, and the this only this path will be the maximum, which will have the maximum 42. So you need to return this sum only, the max sum you need to return of all the out of all the paths, right? So brute force, simple, like the first brute force method. If this is asked in your interview, you need to first explain the brute force method. Basically, if you have 1 point to given 1 point, right, you need to find, you can find multiple paths here, right, which will be brute force, and you can just compare and basically do all that, right, which will cost you a lot of time, complexity of O of n square, because you need to go and combinations, right? So for this you need to know two things, like to optimize this. First you need to solve these questions, max height and width of any kind of tree. Then you can do some similar recursion way. Let's say we have one value, we have this and this, right, L and R. So let's say that we have this this has some value, right, value, this node has some value. What if I find here, what if I find the maximum, what if I find the maximum of this, like if there are or more trees, what if I find the maximum sum of this side and I found maximum of this side? What can be my final answer then? I can, simple, it's 1. It can be not 1, it will be val, right, val plus basically this value plus maximum, yeah, max of L plus max of R, right? But this will give you a lot of values, right? So we need to find the maximum of it, right? We will run the max of it. Got it? So basically this is how we will be doing it. And to do this, you need to find, basically for finding out this path maximum L, you need to basically find the height of the tree, right? And height, max height, basically you can find using this. If you have done this question, then you can easily find the max LR, and then you can just use this method to just get the maximum sum. So this is how you'll do the max path sum. So this is also kind of your like your homework only, right? I just explained you the approach, right? Approach. right? So actually it is famous question. Now we will start with another kind of concept, which is of binary search tree. Another important, very important concept, right? So what exactly is a binary search tree? Let's just do this. You can see here that binary search tree, basically this is a binary search tree. What exactly binary search tree? So let's say that this is a node, right? It's very easy. This is L, this is R. The values should follow in this way. L should be less than N, N's value, and this R should be greater than N. So this is a binary search tree. This will be the pattern. You can see this example where, like, let's say that this 8, 10 is greater than 8, 3 is smaller than 8, right? So this is the full pattern. 14, 13 is smaller than 14, so it comes in the left side, and whichever is the greater, it will come in the right side, like 10, 6, 7, 3, that. This is a binary search tree, right? Yeah. So in all binary search trees, all heights are, in the terms of, you can just write it down here. I will just write it down. All where is it? all all heights are log of base n. Why am I saying this? Because let's say that because we are traversing, basically the creation of this search tree is being done, considering all the, possible nodes, left and right nodes. You there won't be a single binary search tree like this, like a skew tree. So this won't be the case, and for this it's basically of n, right? Because it depends on the height, right, as I told. So all heights are of log of 2n, because it takes all the maximum width as possible, right? You can understand in that way. Fine. Now next concept we will learn about, basically the search in binary search tree. Like how you can search for a particular element. So let me just write that as well. uh, Searching in BST. Fine. So let me quickly draw one more tree, or I can just take this uh, same tree, search in binary tree, right? So this is a tree, uh, yeah, and I need to basically search a particular element. Let's say that we need to search node 10, right? Node 10 you need to search. So searching, so first, like, if we were talking about BT, like only binary tree, the searching would have costed you of n times, because you might have to basically, there's no relation in the binary tree, there's no relation of nodes and rows of it, right? So like even this can be greater than this left can be greater than maybe the right term, right? So you need to traverse all the n number of nodes, right, in a binary, so it will take you off n space. But here, like it's kind of like a binary search, right? Binary search, it kinds of like it has some relation. So this will mostly take log of n, log to power n, O of log n it will take, basically, right? Because it's like a binary search only in an array we used to do, right? So this is how we will do. uh, Simple way, like let's say that we need to what search for 10, right? So we'll see 8, okay. Okay, let's search for some other method, other, let's say 14, okay. Let's search for 14, right? So let's say we are at 8, so we know that we need to get 14, right? So should it be in the left side or the right side compared with 8? 8 is smaller than 14, and so we need to go higher than 8, right? So there's no point of going to this, because this has smaller elements. So this subtree we don't need to consider it, right? So we'll go here. Hence 10, now 14, you'll get eventually 14. So basically discarding the space, search space, right? So hence it will take lesser time, right? Because we know the relations, right? Now I will just write quickly, I will just write the code of it. It's actually really direct and kind of similar. So let's say that we have one function, we are given a tree node, basically star root. right? We are just giving a root, and we are also given a value which we need to basically search, right? Now I can write while root is not equal to null, right? And root dot val root dot value is equal to val, right? Unless this happens, just what you need to do, you need to just basically root will be equal to val. You are just checking it, right? So root can write val, uh, sorry, using Java right here, so you can use val, uh, wait, root val, yeah, and which will be root dot left. Basically this is what we need to, and then just return the root, right? It just checks, basically it just checks if the root, if the current pointer, or where we are, is smaller or greater than the left or right, and then just compare. So this is a simple code of it, right? uh, oh, I missed that conditional statement. Actually, I'm just using conditional statement. So if the value is smaller than root of value, then just go to root of left, else go to root dot right. Sorry, I missed it. Yeah, now it makes sense. Yeah, cool. This is the code of it, simple code, not nothing much of it, right? So what else? Yeah, so now doing another question, really easy. Now you need to find seal of uh, seal in BST. Seal value, basically. Let's see what exactly I mean by seal. So let's say that you are given a key, as 8, right? You need to find out the seal value, basically the value, like just what find a value which is just smaller or equal to key. Basically, if this binary has 8, just return 8, or the position of 8, or else just above, just one above than, like how most above than the value given, right? So here in this case 9 is there, right? So which is just greater than 8, so you will return 9. So answer would be 9. How you will do this? Really easy. It is a binary search tree, right? So let's say that you have two things. You have one seal. Let's say that you have defined one seal as -1, find the lowest one, and then you have one key, right? And now you are basically at this, at 10. Fine, seal is -1, this 10. Like we, so um like we are at 10, so we will just make it 10 for now. We'll compare the seal, like right now seal is greater than key, right? But it can, we want it to be smaller, right? Because it as smaller as we want, but it should be greater than key as well, right? Seal is the ultimately the value which we will be returning, but yeah. So we'll be going with small one. How we'll go? We know the smaller one will exist at 10, at here, right? So we'll go to right, right node, right? So we got what, 5. We got our seal as 5, right? So 5 we got. Yeah, we are at 5 right now. So 5 we got, right? Now we see that 5, the seal, current seal is very less than 8, which we need to make it bigger, right? So instead of going to left, we will go to right. Sorry, we will go to left, right? So we are at 6. So we will do 6 again, update the seal value as we are going. Now we will see key is again very much larger than the seal value, right? So we'll go to left, because right, this is nothing but to just to go, to increase the value, we need to go to left, right? So now coming to 9, we are at the ninth position. Now we will see if there any value, we can go more small, right? So we can go to right where there's nothing else. When it hits the null, then just return the current seal value, right? So this is the answer. Yeah, so this is how we will find the answer, and the code for this would be very easy. I will also code it out for you, or write the code here. Fine. So yeah, let's say that we have one function, and I'm given one root, right, and I'm also given one key. Fine. And I will say that int, let's say that we have one seal value as -1. Fine, lowest value you can take. And while root, like while root, is there some root, you can handle that case. If root, if root data or value, whatever, is equal to key, you know, if it is directly equal to key, then the seal would be the root of data, right? And you basically you just return the seal value, because you got that, right? Return the seal, you got the value itself in the tree, so just return it, that there won't be, you know, seal. So if, but now if key is greater than root ka value, we are using data in this case, right? So data, if the key is greater than root data, what we'll do, we will make the root to go, new root to go to what, right? Right, yeah, right. uh, else else what, make the new root to go to left position, because the key might be smaller, right? So we need to go to left position just to get the bigger one, bigger value, right? Now just return your seal value, you like, unless like it will just get out once the it will reach the null, it will just get out the of the this while loop, and you will get the required seal. Got it? So this is how you will do the seal question. Now homework for you guys, uh, it is again very, I mean, if you understood this, then this will be the piece of cake for you all, to find what, find floor value of given key, right? And then there will be one more homework for you all, which will be insertion in a BST. Now I have made one separate reel of insertion in a BST, right? Which is basically, I will just provide you the link. Link will be in description. Fine, link in description of this video, right? So please go, like first try insertion BST, and then if you're not, then just check that link in description. I have made a reel on this insertion BST. Fine, so you will find that in the description. Got it? So yeah, just check these videos out. And now the last question is really good question. Oh, before that, just hold on. There are two other homeworks which I want to give you, like validate a BST, and also zigzag traversal in tree. So even for these two videos, even for these two questions, I have made the video. Fine. So you want, oh wait, how can I remove this? Okay, never mind. So even for these two, I made the video. The same would be in the link in description. But first, just try it out, all these questions. If you still find difficulties in them, try to basically come up with some, take some time. If not more, just don't take more than 40 minutes. If like it is costing you more than 40 minutes, just jump to the solution, because you don't have to waste more time on this same question. So just check, link and will be in the description. Check these videos out, right? uh, yeah. So yeah, there's one more question I want to just point it out, which will be minimum time to burn a BT from any node, basically. This is a challenge question for you all. right? This is a really challenge question. If you are, familiar with data structures, hash maps as well, like advanced, this is actually really an advanced question. If you found, like, if you reach till here, right, inform in the Telegram channel if you want another separate video for this, because this will take one different video, right? So please, if you reach till here, if you are watching this, reach till here, please let me know in the Telegram channel that if you want a separate video on this question. Fine, so it's a very good question. So till now, just try out whatever I have taught you today, and yeah, see you in the next class. Thank you.